Hello, everyone, and thank you for joining the AstrumDrive podcast. As usual, we're joined by Nelson, the head of our physics department, and today we're going to review Sprint 10 and 11. So, Nelson, please go ahead. Please give us a short update about what did we do during Sprint 10 and 11.
Hello, everyone. Thank you, Bailo. Yes, well, mostly what we did during this couple of sprints was writing the article, which I'm very happy to say that I think we are almost done. We're just reviewing a bit of the language, basically. This is the English good, is well expressed, everything. So it was a nice sprint. We learned a lot. I'm very happy with that. And I think very soon you will able to see it published, hopefully, fingers crossed. So, but during sprint trend, the sprint 10 specifically, we work a lot about the article. We work on the introduction of the article. We work about the field equations, putting everything together, separating in sections, specific sections that we thought will put everything more clear to a reader, and writing some motivation. This motivation that came from what was the idea initially with the metric we were proposing, and how it's a bit different to other metrics, and how also to motivate this metric in terms of Bobrik's work of last year, using their proposal about what a word metric should have. And it was very nice to put that together. And also it led us in very nice directions to discuss about what is going on with the metric in other instance. For example, what's happening with extrinsic curvature here. This is something that we didn't answer yet, but it led us in nice questions, asking nice questions, because you start writing and you start discussing. It's happening all the time. Also, we wrote a lot about how anisotropy enters into the uh, the system we're imagining, because we're putting some general matter, general in the sense that it's really a perfect fluid, but it's generalized in the sense that it's dependent of some coefficients, and there are some generalizations. In these generalizations allows for anisotropy, and it can tell us, I mean, the coefficients has to be this or that, and everything, I think, work nicely. But we also uh, we have the idea of writing some special cases, because at the end uh, we have the article and we have everything done, but we never really solve Einstein's equations. We have Einstein's equations, and we have to put specific cases in order to see what's going on with this. What I mean is, like, you choose a equation of state, and then you solve using some parameters, and then you have to solve the differential equations. um, we reviewed this, and we decided that it worth uh, an article by itself, because it's a lot of work, and it could be a lot of interesting results here. So basically, we also this the writing the article also led us in that direction, to decide that we have something else to say, and it's large enough to deserve its own article. And that's basically what we did in this in the spring. Well, no, there's one more thing that I think you will find interesting, because we also work a little about this problem using a general lapse function that we're figuring out how it works, and we start working on that in Cartesian coordinate, using x, y, and z coordinates, and it's a lot of more complicated, a lot more complicated, because the questions are really messy, and even if you're using Mathematica, figure out how to work out the questions, it's it's messy. Yes, I think that's the word. But we found that there are nice things we consider, and probably are a bit different from the case of the spherical symmetric space-time, and we believe we might have something there. And this, I believe, I by myself, I'm not speaking in the name of the whole group now, is that it's because there is not it's not a direct mapping between these two metrics. Although both are quite similar in many senses, they are not the same. There is no just a single transformation that you do and go to one to another. At least not the usual transformations. So far, we haven't figured out a transformation to go from one to another. But it is very nice. There's some results there. At least this is of what we did during Sprint 10. Uh, if you want, I can just go on Sprint 11.
Yes, Nelson,
So
let's
on Sprint 11,
sure. Let me just switch
yeah,
the screen.
okay, good.
Please go ahead.
Sprint 11 was
Go ahead, Nelson.
was exciting. Yes, Vale was very exciting because we finished the article in Sprint 11, and we work all the items that I told you in the 10th sprint. We work it out again. We work on the conclusions. We work again, finishing the introduction, the details, more discussion. We did a lot of discussion about uh, uh, the energy conditions, and there is a lot that is going on there. New ideas, discussions about what does these energy conditions mean in general. I mean, we know what they mean in a specific context, but is it as general as they claim? Maybe a couple of them are in general enough, but not all of them. So it depends of the system, and we know because it's been published and it's been proved and it's been also tested in experiments that some systems violate some of these conditions, and that's something we have to take into account. So there was a lot of work going on in there. That's because we take into account the energy conditions in our system, and we find out that at least in the way that the metric is written, is we fulfill most of them, most of the energy conditions. Uh, uh, we fulfill them. It's not maybe the most interesting way, but the point is that they are physical, and that's good. That's good. But we have to work more on that. One of the things is also we did during this sprint was like in order to understand how to work out these special cases, we started working on how to solve the partial differential equations. And this is a hard task. It's about talking of a system of coupled differential equations, partial coupled differential equations, and it's not an easy way to solve these systems. It's been a lot of work, mathematicians, coders, working on several languages, working on this. There is not just a single way of working out. Uh, we are not really experts in solving numerically, and we're working on this. But we started reviewing some libraries, specifically Python libraries, that we think might help us. At the end, we find out that these libraries are not so what's the word, extent, or they're not so wide, so that we can include most of the formulations we are using. I mean, the way of these equations are formed as quite non-linear, so it's quite difficult to solve these equations. But still, we're looking for more. If you have any recommendations, please let us know in the comments. But still, we're working on that. We're working on this. So not writing the code from the very beginning, because we know a lot of people have been working on this for a long time. We want to uh, take advantage of this and cite these colleagues that probably make a lot of work. And basically that's it. We work it out all this together, and we also set, I think this is the final comment, the starting point for working in what we think is going to be the future, which is physics-based deep learning for the next step in the working on the warp drive, which is also could be a work of solving differential equations in this case. But okay, this is something that is still in our next, not distant future, but we're still not there.
Thank you very much, Nelson. And you spoke about articles, so we're currently reviewing it, and probably we're going to send it for publishing in the beginning of the next week. And Nelson, do you mind to talk a little bit about our current plans for the upcoming sprint?
Sure. Okay. Yeah, this next spring is quite exciting. Now that we work at the article, then we have more time to work on some other things. One of the most interesting things to this sprint is like we, well, there are several, but let me go on the one that I find very interesting in the short term, which is now we have the labs function, a general labs function. We already find out, you can check in the previous sprints, we already find out that using this general labs function, it allows for some other terms in the energy momentum tensor. And this, uh, for instance, dissipation, heat flux, and so on. So what we are trying to figure out now is like, well, what does this mean in terms of the energy conditions? And that's a quite interesting question. But one of the things that also is implying this, asking this question is, which is the right observer? Which one is the observer that is looking at this? I think we have a simple answer and a complicated answer, but still we think it's quite exciting. At least for me, it's quite exciting because it's like exactly the point. What is it? What we have so far here is good enough. Is helping us with no violating some of the energy conditions. At least working out the amount of energy density we have. We still have some problems with energy density, but there is a lot here to say. Where this one is very interesting for me. Also, we are working out some other interesting tickets. For us, for instance, we're going to explore what's going on uh, with the magnetic fields when if we implement magnetic fields in this system, which is, well, you have basically two scenarios. You have a lapse function, which is equals to 1, and a general lapse function, or at least a lapse function that is not time dependent, but is position dependent. So in that sense, we can have a time like killing vector in the system, which is important for the symmetry for us, at least at this moment. So in that sense, in those two scenarios, how can you plug in magnetic fields? What's going on with magnetic fields here, and how these magnetic fields are going to be? We're starting to explore this because these magnetic fields or these electromagnetic fields that could be static, could be just space dependent, time dependent. If they're time dependent, it means they have dynamics. If they have dynamics, the problem is is quite different problems. So each one of these we're going to work it out separately as we should, but it's quite exciting to see how they're going to enter into the system, how they now start uh, contributing of what is the matter in the system. So we think it's very exciting also that we, of course, we have all the tickets. We have this interesting ticket, which is probably close related or not, but this is a ticket that is it's I think it's an old question, but there's a question that uh, we didn't find this answer anywhere, which is what's going on when you have a mass, and you can find this in Reddit forums and so on. When you have a mass and this mass is start moving in a empty space universe, you start moving this mass very fast, and you just have one observer, and this observer is looking at the mass. It rests with respect to some reference, and the mass is moving, and it start moving faster and faster. So you have some special relativistic effects on this mass, and this one of them is like you have contraction of the length contraction, you have time dilation, and these things act on the mass in terms of the one of the servers. So what happens in the limits? What happens when you start going faster and faster? What's going on with the mass? What's going on from the point of view of this observer with something that might get in up to the limit of getting closer to the speed of light that you cannot ignore what's going on with space-time there, or maybe how this is reflecting in the space-time surrounding the mass. We're looking into this because we don't know the answer, and this might be related to how to connect observers in these situations where we have warp velocities in warp motion, and how the bubbles are behaving with respect to observers, or even we can have deeper questions or deeper answers regarding what's the connection of this space-time in general relativity and something that comes from a flat space-time, which is in special relativity. Uh, at least at this moment, we didn't find anything good, at least good or published about this topic, which, if you think about it, it seems almost like a student question that any student can ask in the class. But I asked some of my colleagues, and nobody ever think about this before. It's like a question that is not useful for researching. It's not useful for teaching, apparently. So nobody asked it. So it's a good question to ask. I'm happy to. I'm going to be really happy to see what's going on there, and how this connects with where we're doing. And if it's not connected anyway, it's a very interesting question to see. I think we might have some insights there. Uh, and also during this spring, we are going to start working now for real with the first examples of what is the physics tips based deep learning, which is in Python and all these machine learning techniques. We're starting with some sample to work it out and to see how to start, how's going to we're going to enter into this field of using machine learning to work out the first solutions with a more general system with open parameters and some code that can help us learning how to solve this and find the optimal set of parameters for the physical situation we're looking for.
Thank you very much, Nelson. So just to make a summary, what we're going to do during the upcoming sprint. So the first thing, we're going to expand our understanding about the warp drives by including the heat dissipation equations, and also by exploring how can we include the electromagnetic force in the warp drives, because we found some evidences that the electromagnetic force and the electromagnetic fields may be the key of us retrieving positive energy solutions. So we're really excited to start looking in this direction. And at the same time, as we promised, we started looking in different libraries how to automate um, the solution of the calculations of different equations and differential equations. And in the same time, we want to explore, can we use neural networks to resolve these equations? Because as you guys know, there are a lot of solutions. I mean, not a lot of solutions, but at least several solutions of the Einstein equations, including the Alcubierre solution, which are correct solutions, but they are not physical because they require a lot of negative energy. So we want to start exploring hundreds of thousands of solutions, and we want to automate their calculations. So this is the reason why we are going in this direction with neural networks and also machine learning for differential equations. So really exciting sprint. And Nelson, thank you very much for the resume you did. Do you want to say anything else before we close for today?
I would like to say that I want to thank to all these guys, this person that have been commenting in the videos and sending us the best wishes and also some nice inputs. I mean, recommended papers, ideas. It's quite nice to read you guys, and we're looking forward for more of this, and we're paying attention of what you're saying. Thank you.
Thank you indeed. So we really got some really nice comments and reference papers. So guys, thank you for your support. And if you like our work, please like, share the video, and you can become our Patreon as well. Links are below. And with that, thank you very much for listening, and let me wish all of you to have a very nice and successful week.